Okay, we said, all right, when we're talking about NO formation, it's not happening in a single step, but it's actually happening in two steps. Okay, and if you look at these two together, right? So N2 plus O giving NO plus N, and O2 plus N giving NO plus O. When you sum them up, basically the nitrogen which is being formed in the first reaction, Z1, is getting consumed in the second reaction, as we discussed. Okay, and the oxygen atom which is getting formed in the second reaction is getting consumed in the first reaction. So essentially, if you look at net the reactants that you have N2 plus O2, and they're leading to the formation of NO molecule in Z1 and NO molecule in Z2. So essentially, NO plus NO or 2NO, which is the basic reaction we want to use to come up with the expression for the rate of formation of NO itself, right? So now the only thing is this reaction, as I said, is just some sort of a global reaction, and what we will do in the next few slides is essentially apply all the approximations which make sense to reduce and come up with a simplistic expression. Okay, so now when we look at this particular uh, set of equations, we can write down the uh, rate of formation of NO from here, right? So both are leading to the formation of NO, but these reactions can happen both in the forward and the backward directions, right? These are elementary reactions. So here, so one thing about reactions, when you see an equal sign like what we have here, this is one another way of telling you that these reactions are reversible, right? And we basically discussed that when we talk about elementary reactions in general are reversible. Almost all elementary reactions are reversible. Only at certain conditions you can come up with and say that, okay, maybe it's not going to happen in the backward direction, right? It just happens in the forward direction. So under certain conditions, they are just proceeding in one direction, but in general, you can say they're bidirectional. So now, without having any specific assumption about the directionality of the equation, let's just write the net rate of formation of NO, right? So if you want to write the net rate of formation of NO, it's going to be equal to its rate of formation minus its rate of consumption. Okay, so this first reaction at Z1. So the forward direction, we'll call the reaction rate coefficient Z1F. Okay, it's happening in the direction, in the forward direction. Backward meaning these are the products become the reactants. In the backward direction, we'll call this as KZ1B. Okay, same way for the second reaction. Forward direction, we'll call it as KZ2F, and backward direction, we'll call it as KZ2B. So here, when we look at the rate of formation, well, NO is being formed in both in both of these reactions, Z1 and Z2. All right. So we can simply write it as equal to the rate of formation of NO in this particular reaction. Z1 is in the forward direction is the reaction rate coefficient KZ1F times the product of the concentration of the reactants, right? Which is N2 is one reactant, oxygen atom is another reactant. Okay, so this is the formation from reaction Z1. From reaction Z2, we can write it as KZ2F, right? The reaction rate coefficient for the second reaction times the reactants, which is O2 times N. Okay, and what the way we have written this is simply by following the law of mass action that we discussed before, right? We said, okay, the reaction rate can simply, or the rate of formation can simply be written in terms of its stoichiometric coefficients and reaction rate coefficient. So that's essentially what we're following. So this is how the NO is being formed. But because these reaction rates are bidirectional, they can go in the forward and the backward directions. It can also get consumed, right? When we look at the backward direction of this particular rate, NO plus N can get consumed to form N2, N2 and O. Okay, so then what we will do is, okay, this is the formation. Now let's talk about consumption. Consumption would be minus K Z1B. Uh, in the reverse direction, the reaction rate coefficient will be different, right? Reaction rate coefficient is K. And this times the reactants. Reactants now would be NO times N, okay? Minus K Z2B. Again, the the reactants will be NO times O for the reverse of Z2. Okay, so these are the reactants and they're going in the backward direction. So this is the net formation rate, you could say. The first two describe the formation, and the last two, which depend on the concentration of NO molecule, describe the rate of consumption. Now, what we can do is we can make an assumption about the directionality of this particular reaction, and we say that, okay, you know what, the the uh, the backward reaction rate for these two reactions, Z1 and Z2, is almost zero, right? We can say that the only way when we talk about NO, it's only being formed, but it's not really being consumed, right? So what we're essentially saying is that we're saying these two rates that we spoke about, the backward directions, the reactions are not really happening. Okay, it's they're almost negligible. And this is really real. This is very much true when we are talking about the initial stages of a flame, right? In an initial stage of a flame, the you have some oxygen atom. It's starting to attack the nitrogen molecule. So you just formed some amount of NO. You don't have a lot of NO to begin with, right? So nitrogen was inert as the flame went on. You just started at high temperature. You started to form some NO. So in places or in regions of the flame where NO concentration is small, or it's almost zero, at that point you can simply say that, you know, this backward reaction rate depends on what? It depends on concentration of NO and concentration of N. If concentration of NO is almost zero, then this backward rate is zero, right? Both in Z1 as well as Z2. So this is an assumption that we apply, and we say, okay, no, these two reactions are only happening in the forward direction. So this is the first assumption that we spoke about. We are making an assumption about the directionality of the reaction. Okay, and it's a reasonable assumption in the initial stages. Okay, or in places where the NO concentration is small. And if you make that assumption, then what you can say is that the rate of formation of NO, which is basically what we are after, is simply equal to the rate of formation from the two reactions. So KZ1F times N2 times O plus KZ2F times O2 times N. Okay. Now, this is what we have, but if you compare it with the kind of expression we wanted to have, I said we wanted to have something like dNO by dt is some K times N2 raised to P times O2 raised to Q, right? We wanted to have something like this. And the reason we want to have something like this is it's very simple. We can say, okay, we have this we have this one-step reaction mechanism. N2 plus O2 gives 2NO. Okay, it's not happening in a single step. It's happening in multiple steps as we see here. But we can, by effectively applying some assumptions, we can come up with this expression right here for the rate of formation of NO. Now, if you compare this equation that we want, let's call it equation 1 and equation A, what you will see is that we have N2 in here, we have O2 in here, but we also have two other species. We have oxygen atom and we have nitrogen atom and their concentrations. So now what we will do is we will use the remaining approximations, the steady state approximation and partial equilibrium approximation, to figure out a way of removing or writing the concentrations for oxygen atom and nitrogen atoms in terms of as a function of the concentration of N2 and O2. And if we do that, then what we will be able to do is we will be able to come up with an expression for the formation rate of NO, which is this one, in terms of some reaction rate coefficient times the concentration of only N2 and O2, which is essentially what we want to make it really simple. Okay, So now let's move forward in that direction, and let's try to do it one at a time. Any questions up to this point? Okay. Uh, I hope you guys are there and it's all
Yes,
clear.
yes, doctor.
Okay,
No, no,
great.
it's clear. It's clear.
Yeah,
Thank you.
doctor, we are here.
Okay,
Yeah.
I know you're there. I just wanted to hear your voice. Everyone was very quiet.
No, it's
Okay.
clear. Doctor, it's clear.
Okay, Khalas. Now let's go on to the next step. Okay. So this is what we had in the last part. Uh, so we were able to, by making an assumption about the directionality of the reaction, by just saying that it's only happening in the forward direction, we were able to write the formation rate of NO in terms of these two terms, right? Z1 and Z2, which represent the two reactions which are happening. Now, let's try and remove this nitrogen atom, and let's try to write it in terms of the N2 and O2 and maybe O also if needed, right? But let's try to write it in terms of the remaining terms, the remaining concentrations that we have here. So now when we look at the nitrogen atom, right, we said, okay, in the first reaction, you have N2 molecule being attacked by this oxygen atom, and you get nitric oxide uh, plus N, the nitrogen atom. And we said this reaction is slow, okay? But as soon as this reaction occurs and this nitrogen atom is formed, the nitrogen atom goes and attacks an oxygen molecule, and you have the second reaction happening. So when you look at this description of what is happening here, you can very well imagine that as soon as the nitrogen is formed in the first reaction, it gets consumed in the second reaction. So you can effectively say that the second reaction, the reaction that consumes nitrogen, is so fast as compared to the first reaction, that its concentration is remaining more or less constant, right? It's remaining small and it's remaining more or less constant. So whenever you have a situation where you could say that the rate of formation is almost equal to the rate of consumption, or you say, okay, as soon as the thing is formed, it gets consumed, which also satisfies this equation. Rate of formation will be equal to rate of consumption, because once it's consumed, there's nothing left. You have to form it again, and whatever you form, it gets consumed again. So since it satisfies the observation for the nitrogen atom in this particular case, we can very well go ahead and say, since the rate of formation is equal to rate of consumption for nitrogen atom, the nitrogen atom concentration does not change, right? And essentially, then we can basically write it down as the rate of formation is equal to rate of consumption, okay? Which are essentially two related to each other. If rate of formation is equal to rate of consumption, then its concentration is not changing. Okay, so let's try to do that for nitrogen atom. So rate of formation of nitrogen atom from the first reaction, it's getting formed. So it's KZ1F times N2 times O. And then once it's formed, it's getting consumed in the second reaction. Okay, so it's getting consumed, so it's going to be minus K Z2F N times O2. Okay, so this is what we have. But since this forward rate or rate of production is exactly equal to its rate of consumption, what we can simply write it as, we can write it as K Z1F times N2 times O is equal to K Z2F times O2 times N. Now remember, we are doing all of this because we want to write an expression for nitrogen atom in terms of the rest. Okay, so we can send this thing to the bottom here, and we get an expression for nitrogen atom as equal to KZ1F times N2 times O, what is what we have here, rate of formation, divided by KZ2F times O2. So by using this steady state approximation, which is very reasonable, which is exactly how the nitrogen atom is behaving here in this particular set of reactions, we are able to write the concentration of nitrogen atoms in terms of the remaining species and the rates at which they are progressing. So now once you're able to write an expression for nitrogen atom in terms of the other species, we can simply use this and replace the nitrogen atom in this particular equation A. Okay, so the first term remains as it is. All right, there's no nitrogen atom in there. The second term becomes something like K Z2F times O2 times N. Now what is N? N is this quantity. So let's write this quantity here. N is K Z1F times N2 times O divided by KZ2F times O2. Now, concentration of O2 gets cancelled, KZ2F gets cancelled. What you're left with is KZ1F times N2 times O, which is exactly what you have in the first part. So you essentially have KZ1F times N2 times O plus KZ1F times N2 times O. So essentially, this equation A, once we write the expression for, once we apply the steady state approximation for nitrogen atom, it becomes equal to 2 times KZ1F times N2 times O. So now we have become successful in removing nitrogen atom, right, from this equation. And we have now a rather simple equation for the rate of formation of NO, right? And here we have although eliminated the nitrogen atom, and although we may think that okay, the reaction rate coefficient Z2F is gone here, but in reality the reaction rate Z2F is being is still showing its effect in terms of the fact that now the Z1F, instead of being KZ 1 times KZ1F, it's 2 times KZ1F times N2 times O, right? And it's essentially the fact that we have 2 times this rate here indicates the fact that the presence of Z2 is still there, and simply the fact that Z1 is so slow is the rate determining step. So the the reaction rate for Z2 is sort of being replaced by the reaction rate for Z1. So uh, this uh, is another simple. This is basically the simplified version by just putting another assumption, another very reasonable assumption. Okay, but when we look at this, we are close to our goal. We have still not reached our goal, right? Our goal was to write this expression in terms of O2 concentration for O2, because well, O2 is the other reactant that we have, a stable molecule whose concentration we will know very easily. Okay, so now we have this expression, equation B, and now we have to figure out a way of getting rid of this O, or in simple terms, we need to write replace the oxygen atom concentration in terms of concentration of N2 and O2, or maybe this concentration of O2, right? We somehow have to replace this oxygen atom. That's the simple goal here. Okay. So we did the steady state approximation. We also did the directionality approximation by assuming only the forward direction. So now we are left with partial equilibrium assumption. Okay, so now let's keep this in mind and move on to the last assumption. So this is the equation we had, right? Equation B, rate of formation of NO is 2 times KZ1F times N2 times O. And what is Z1F? Well, Z1F is simply corresponding to the first reaction, which basically says that N2 plus oxygen atom is equal to uh, NO plus N, right? So this one was the reaction Z1. Now, when we are talking about this last approximation, this partial equilibrium approximation, it's important to understand its limitation and how it is applied. Okay, so when we spoke about steady state approximation, we were applying steady state approximation to a species. The species involved was nitrogen atom. We said, okay, the rate of change of nitrogen atom is 0, and so we applied the steady state approximation. We can also apply to any other species that you see behaving like the nitrogen atom in this particular case, right? As long as its concentration is steady, you can go ahead and apply steady state approximation. But when we talk about partial equilibrium assumption or partial equilibrium approximation, we apply this partial equilibrium assumption to a particular reaction, okay? Only to a reaction. it does not, we are not applying it to a species. Okay. So this is a very important part here. And what does it mean by partial equilibrium assumption? We are basically saying that the rate of forward reaction is equal to the rate of the backward reaction for a particular reaction. Okay. So, and again, as with all other assumptions, this assumption as well, this partial equilibrium assumption, is valid under certain conditions. Okay, in generally speaking. Okay, and so as long as you're under those conditions, the simplification will perfectly work. All right, you don't have to worry about anything else. It's again a physics-based assumption that we are making. So now, when does partial equilibrium assumption apply? Well, it applies in a lot of cases where the the forward and the backward reactions are progressing really rapidly, and the rates of forward reaction are equal to the rate of the backward reaction. Now, a particular case where this is true for the reaction that we are looking for is the dissociation of oxygen molecule into two oxygen atoms. Okay, so this dissociation reaction of O2 to two oxygen atoms, it's a reversible reaction. It happens both ways, and it's this reaction is in partial equilibrium, right? Species is not in partial equilibrium. So this reaction is in partial equilibrium, meaning the rates of the forward rate of the reaction is equal to the backward rate. So when we talk about the forward rate of the reaction, forward rate of the reaction is the reaction rate coefficient K times the concentration of the reactant, right? The reactant is just O2. So here, when we're looking at this particular reaction, we are simply saying forward rate is equal to backward rate under equilibrium assumption. And so forward rate would be K. Now this reaction is Z4, this dissociation reaction. So K is Z4F, forward direction, times concentration of O2 is equal to K Z4B times now we have two oxygen atoms being produced, right? So it's like concentration of O times concentration of O, right? So O plus O, if you want to think about it, or O square. Okay. So now what we have is we have an expression for oxygen atom concentration in terms of O2. Okay. So we can write it as O square by O2 is KZ4F by KZ4B, or more importantly, all we care about is the concentration of oxygen atom. So concentration of oxygen atom, we can send this to the right-hand side. It becomes equal to the square root of this ratio of reaction rate, KZ4F by KZ4B, which, if you recall correctly, is also the equilibrium constant for this particular decomposition reaction, right? Kc raised to half times square root of the concentration of O2. So now by doing this, what we have is we have removed all the nitrogen or and oxygen atoms from this reaction rate expression, or the rate of formation expression for NO. So now once we have this expression for oxygen atom concentration, we can substitute it back in this equation B. Okay, so what do we have here? Equation B, we wrote it as dNO by dt is 2 K Z1F times N2 times concentration of O atom. Concentration of O atom is this quantity. So K Z4F by K Z4B raised to half times O2 raised to half. Okay, and now what you can do is, okay, these reaction rate coefficients, we can put all of them together and write the molecular concentrations together. So we can rearrange this and we can get this expression here where 2 KZ1F times these reaction rate coefficients all can be taken as one big K, okay, times N2 times O2 raised to half. So now this expression that we have here, equation D, is our reduced model for NO production, right? So if you think about the reduced equation, N2 plus O2 giving 2NO, we have been able to more or less use this, use the actual equations, the two steps, and by applying simplifying assumptions, we have been able to come up with a one-step global mechanism to represent the NO formation, and uh, it it is in this state where we write it as K dNO, the rate of formation of NO is equal to some reaction rate coefficients, which is this product of these three things, times N2, right? It's raised to 1, as we see as the stoichiometric coefficients of nitrogen on the reactant side. But O2 is not raised to 1. O2 is raised to half. And we see why O2 is raised to half, right? As we applied the partial equilibrium assumption. So now, when you look at this, you can very well see that this is more or less the expression that we wanted to come up with. And this expression is much more sensible, much more valid at wider range of conditions than a one-step mechanism that you can come up by simply looking at by simply doing experiments. Okay, so now there are a lot of cases where for different set of reactions under different range of temperatures and pressures, people like to identify what are the species that for which you can apply a steady state approximation, what are the reactions which can be under partial equilibrium, and they try to come up with a simplifying expression like this. And it's not always possible, of course, but there are some cases where it's possible. Okay, and here we were able to do it because first we had a beautiful set of reactions which for which we could apply these set of assumptions that we spoke about, and the reaction was small. It was only a 2 to 3 step reaction mechanism. Okay, and yeah, so this is a very good example where some things can be done. You can do it for similarly small reaction mechanisms. You can reduce them in this fashion and come up with a simplistic expression. And once you have this expression, then you can sort of gain a lot of physical insights by looking at by playing around with the rates or by calculating the rate coefficients and looking at how things change with the concentration, right? And in reality, a lot of times we are not able to do this, especially when the mechanisms are very large. And in those cases, we have to rely on something like a computer program, something like ChemCan or Cantera or others, which follow the same methods that we have been discussing in the class. But of course, instead of doing it manually, it's happening using the code, and which is easier, of course. But the key point of doing all this is to make sure that you understand how we get this thing done, and you are confident to reduce a given set of reactions into something smaller by making these approximations, right? These approximations are valid. Only the thing is you have to identify under the conditions of interest or your whatever pressure and temperature that you're interested in, you have to sort of identify which one of the species that you're looking for behaves like a steady state species. You have to identify what are the equations which behave, which are under equilibrium, which tend to behave almost like they're under equilibrium. And once you're able to come up with that, then you can reduce any given mechanism and come up with smaller things. It's not trivial, of course. It requires practice and stuff, but this is essentially how it's done, right? So if this is something that's part of your thesis, or if there's something that you want to do, so what we completed now is a starting point. It's a very good starting point. You just have to use a similar methods and go on further with this. Normally, what also is typically done is once you have a given reaction mechanism, these same sets of approximations, same concepts are sort of used to reduce it and then come up with a proper sensitivity analysis to see, okay, which is the most important reaction and what can I do to minimize the formation of, in this case, we want to minimize formation of NO, right? In some cases, we may be looking at minimizing formation of something else, right? So, or maximizing the production of something else. So basically, you have to understand what mechanisms are there, what is the route it is following, so that you can play around with it. Okay, play around with the rates, play around with the species involved, and try and reduce it. So in this particular case, it's very obvious that if you want to reduce the formation of NO, you have to reduce these rates, right? The Z1 and the Z4. Z4 is a dissociation. So dissociation happens at high temperatures. If you reduce the temperature, this KZ4 is already going down. Okay. And KZ1F is basically N2 plus O, giving NO plus O. This oxygen atom also comes from some sort of dissociation, the oxygen atom being oxygen molecule O2 being attacked by some radical species. So this also tends to happen at high temperature. So a very, very quick way of reducing the nitric oxide formation is by reducing temperature.